Today's lesson is called Approximating Area. So the areas that we not have found at this point are some geometric shapes, such as a rectangular shape, which is length times width, triangle, which is a 1/2 times height times the base of the triangle, circles, which is pi times radius squared. But our goal today is to figure out how to calculate area of a curvature function. So something that has a curve. Beside the circle, rectangular shape or triangle or any other shape that you have dealt with before, whether it's trapezoid and so on, it was a straight line. So imagine if you have a function like this and you want to find the area of this region. To start off, instead of finding the exact value of the area, we're going to try to approximate it. And to approximate, we're going to use rectangular shape. So let's pretend that we have f of x that looks like a parabola. And our goal is to approximate the area from A to B. And like we mentioned before, we're going to try to use rectangular shape to approximate it. So we're going to try to fit rectangular shape in between those regions to calculate the approximation. So it will look like this. You're adding x amount of rectangular shape. So delta x in this case represent the width of the rectangular shape. And we're going to try to keep the rectangular shape even width. Therefore, it'll be easier to calculate. So if you want to find the area of A to B, the width of the rectangular shape will be the difference in space over the number of rectangles you're trying to fit into that space. So it'll be B minus A over N. N in this case will be the number of rectangular shape in between A to B. So let's look at an example to calculate the area. Example 1. Using 4 left endpoints of rectangles to approximate the area of the region lying between the graph of negative x squared plus 4, x-axis, and between x equal to 0 to x equal to 2. So the key point in this case is using left endpoint of the rectangular shape. Just keep in mind there's some different ways to draw the rectangular shape within A to B. In this case, we'll be using left endpoint. On our next example, we're going to use a right endpoint. We have negative x squared plus 4. So here is our x-axis. And we have a parabola where y-intercept is 4 and your x-intercept is 2 and negative 2. And again, we want to find the area from 0 to 2, so we're looking at the right side of this. And our goal is to draw a full rectangular shape to approximate the area. So the first thing we should do is figure out the width of each rectangular shape. So notice that we have from 0 to 2 to cover, and we're dealing with 4 rectangular shape. So our delta x will be 2 minus 0 because that's the distance that is provided, and we're going to try to squeeze in 4 rectangular shape. So each rectangular shape have half as a width. So let's say we have 1 here, we have 1/2, and 3 over 2. And you're starting from 0. And you could slowly see this will be your width, and this will be your width of your rectangular shapes. And notice that it says use the left endpoint of the rectangle. So pretend that if this is a rectangular shape, 0 will be your left side of the rectangular. So from 0, we're going to go up to the curve and draw rectangles. And we're going to repeat this for each rectangular shape. So 1/2 to 1 will be the second rectangle. So we're going to use 1/2 to go up and draw rectangle. The third one. the last one. And as you can see, in this case, we cover more than what we needed because we just needed this interior space. As you can see, the right side of the rectangular shape, it comes out a little bit. So our approximate going to be bigger than our exact area. So we know the rectangular shape has an area of length times width, and each width was 1/2. So the first rectangular shape has a width of 1/2 and the height of, or the length of, f of 0. We went to the curve at 0. Second rectangle, once again, you have 1/2 as your width, and this time we use 1/2 to go up to the curve. So this will be, the length will be f of 1/2. Again, with similar concept, we should have the next length to be f1, and the last one will be f of 3/2. And this will be your approximation after calculating this. They all have a equal width, so I'm going to factor out 1/2. F of 0 is when x is equal to 0, so that will represent 4. F of 1/2, this is 15/4. F of 1 is 3. F of 3/2 is 7/4. And there's your 4 length of the rectangular shapes. If you add 4 plus 15/4 plus 3 plus 7/4, it should end up with 25/2. So the area, the rectangular shape in this case, all 4 of them added up will be 25/4. Again, keep in mind this is bigger than the area that we want. Now example 2, same direction as example 1, but instead, this time we're going to use the right endpoint to create it. So we have, once again, negative x squared plus 4. So now, your width will still be the same because we have same distance and we have same amount of rectangular shape, which is 1/2. So 1/2, and 3/2. But in this case, we're going to use a right endpoint. So in example, we use 0 instead of 1/2 because that was the left side of the first rectangular shape. So this time we're going to use 1/2 to create it. So we're going to draw this all the way up to the curve. And the second rectangle is 1/2 and 1. Again, 1 is the right endpoint. And we're going to repeat this process. And the last rectangular shape in this case doesn't exist because 2 happen to be an x-axis. So your length in this case happened to be 0. So visually you only see 3. Technically there's 4 rectangular shape. So as far as the area, all 4 have the same width. So width times, again, the length now. The first rectangular shape, again, we use 1/2 this time, so it'll be f of 1/2. The next rectangular shape is f of 1. The following will be f of 3 over 2. And the last one will be f of 2. Okay, just notice the pattern too. Notice that it's 1/2, 1, 3 over 2. Notice that they're increasing by the width of it. So if you calculate this area, you have 1/2 times f of 1/2 was 15 over 4. F of 1 was 3. F of 3 over 2 is 7 over 4. And f of 2 is 0. So the area is equal to 1/2 times, if you add 15 over 4 plus 3 plus 7 over 4, you will end up with 17 over 2. So your area in this case is 17 over 4. So once again, if you look back to the graph, notice that we have empty space in this case. So you could see that right endpoint for this problem will produce lower sum because you're approximately lower than your exact value. So our exact area has to be somewhere between 17 over 4 and 25 over 4, which was an over approximation from example 1. Example 3, using 20 right endpoints to approximate the area region lying between the f of x of x squared plus 9 and x equal to 0 to 4 and the x-axis. So let's pretend this is 9 here. Graph looks like this. And here's 4. Okay. I'm probably not going to sketch all of them out because again, trying to fit 20 within that 0 to 4 will get a little messy, but I'll just show you guys the beginning, and technically you're supposed to have 20 in there. So starting off, let's figure out the width. You have a distance of 4. And we're going to try to put 20 of them in there. So each rectangular shape should have a width of 1/5. 1/5, 2/5, 3/5. So using the right end point, and on and on and on all the way up to 4. Since the width has to be 1/4, the last one should be 19 over 5. Okay, in between you should have a rectangular shape, and you should have 20 of them in there. If you're trying to write out 20 of them as an area, not only it requires a lot of calculation, but it takes a lot of time. So the method that we use in example 1 and 2 is if you're dealing with small amount of rectangular shapes. So we're going to try to use patterns to figure this out. Notice that because you're using a right end point, you're using your first point should be 1/5, and you're adding each width until you get to 4. And since you're adding of each term, or in this case it will be each rectangular area, we'll be using sigma notation. So I equal to 1 represent the first rectangular shape, and we're going to try to calculate this for 20 of them. And we know that they have width of 1/5. And now we just have to figure out the length. Again, length, it starts at 1/5. Adding another width in this case, which is another 1/5, 2/5, and so on. So you could tell each rectangular shape is increasing by 1/5 starting from 0. So 0 plus 1/5 of I. So the pattern is I over 5 is equal to the area, because this is your width, this is your length. So now we're going to use summation to calculate it. So factor out 1/5. F of I over 5 will be I squared over 25 plus 9 . Find common denominator, which happened to be 25 in this case. So 225 over 25. Again, we have a factor of 1 over 25 is common. And now we could apply the rules for the sigma. Sigma notation from I is equal to 1 to 20 for I squared is n times n plus 1 times 2n plus 1 over 6. So it's 20 plus 21 plus 40 times 41 over 6. For the constant is the constant times your n. Now, if you multiply 20 times 21 times 41 over 6, you should end up with 2,870. 20 times 225 is 4,500. And if you add them together, 7,370 times 1 over 125. They're both divisible by 5. So it comes out to be 1,474 over 25 as your area. Again, looking at the picture, this area is over approximation, that the rectangular has a little bit more than the area that we need. So the area we found is over approximation. And hopefully one additional thing you guys recognize was more rectangular shape we have, the smaller the errors become, because the missing gap or the gap that you're going over will get smaller and smaller and smaller as you add more rectangular shape. So conclusion, to find the area approximation of f of x from a to b given n rectangular shapes, your width could be found by subtracting the two distance and dividing by the number of rectangles provided. Your left endpoint patterns is a plus delta x, which is your width, times I minus 1. That will solve the patterns for the left endpoint you guys could use to find rectangular shape. The right endpoint will be a plus delta x times I. And one additional thing that we recognized doing 3 problems was the lower sum compared to the upper sum. If your function is concave up, left endpoint will produce lower sum, right endpoint will produce upper sum, which means it's over approximating. Concave down will be the other way around. Left endpoint will produce upper sum, right endpoint will produce the lower sum, which means you're under approximating.